So next up we have Bernie, and he's going to, so she's going to be describing free workflow add-ons to improve machine learning reproducibility in astronomy.
I'm Bernie Boscoe, and thank you for having me here at ADAS. And I will be talking today about 3 workflow add-ons to improve machine learning reproducibility in astronomy. So this talk, I'm thinking about small to medium astronomy research groups who might be incorporating machine learning into their workflows or thinking about it, possibly lucky enough to have a computer or data scientist or a tech person on their team, or not, and who are interested in these cultural considerations of crossing domains. For example, what are machine learning needs from industry or from places that are not in astronomy versus what does astronomy need for doing machine learning and the practices and tools that would entail. So a little about me. I'm a computer information scientist. So I work with astronomers and study their data and code practices. So right now I'm working with an astronomy team at UCLA who are doing machine learning projects. And specifically, we're looking at predicting galactic redshifts using photo-Z's and machine learning. So before machine learning, let's go back in time to 1995 at, you guessed it, ADAS. So in the beginning of digital astronomy, what I'm calling it, so maybe we can say this started in the 1970s, astronomers have been designing and building their own instruments and software tools since this time. And most famously, I think, is designing the FITS file format, which has been well represented at these birds of feathers at ADAS over many years, starting in the 1990s. And so during these bird of feathers, they would be debating, do we modify FITS? Do we keep the same? Clearly, we should always have it be backwards compatible. But what does that mean? And what does that look like? And what types of issues are we addressing in the FITS file format? And so I will point this out as one who studies other scientific domains. Most scientific domains do not have their own file format, let alone the plethora of trusted tools built over the years. As you would know, IRAF, FITS, systems like IDL and languages like Fortran used in the process of building these. And so I always tell astronomers they're very spoiled by having this infrastructure, digital infrastructure to use. But now we have seen as it ages over the years, astronomers might be a victim of their own success. Now we have these tools that are well beyond what they were expected to last. And so now new decisions have to be made about what to do about these things. And I write about this. If you're interested, that's one of my papers at the bottom in the history of computing. So one of the research questions that I think about is, for this project anyway, is so when astronomers adopt tools from other open source and industry domains to incorporate into their machine learning research, what can we learn from this, and what does that look like, and what are the pitfalls and what are the benefits of doing such work? And so in particular, I'm studying when astronomers use tools like TensorFlow or PyTorch, as opposed to these bespoke solutions like building them, or astronomers are doing a combination of both. They might be using TensorFlow and building their own C++ algorithms that might go along with TensorFlow. And so this crucial point is something that I've seen and lived and realized over the years, is that most of this machine learning code and these infrastructures and tools, most of anything that you would build now will likely not run in 5 years' time. And our team has done this. We've tried to rerun projects from just a few years ago. For example, the Chalou and Vandenberg exoplanets deep learning project. So that's from 2018, and we had so much trouble even replicating this study. And they were very generous. They gave all of their code and everything in a GitHub repository, and the survey is public, so you would think this would be easy. However, you had these competing libraries, which then you have all of these conflicts. And then do you deprecate one, or do you upgrade the other one, and getting everything to talk to each other when you have all of these dependencies? It was very difficult. So this is just something to consider if you're considering incorporating machine learning into your work. So my first suggestion here is add-on number one, which is versioning training data. And so Evan Jones, my colleague, has a poster in ADAS this year. So it's called Building a Training Set of Hundreds of Thousands of Galaxy Images. So this is this arduous process of how do you get all of these images for a training set? Because as you would imagine, just querying a survey and collecting all of the information, that's not machine learning ready. And to get these things into the form that we need them to is a lot of work. That data munging piece is the part that nobody wants to do, it seems like. And so what we thought about in this is what was done in the initial query, like what were the quality cuts that were done, and then our question was, when do we make a new version? And the granularity is key here. How much changes were made, and then what would that mean in terms of versioning the thing? So we chose to make a new version when the total number of galaxies changed. And for example, we had these redshifts greater than 2.5. They were not very well fit, but we kept them in the version because we wanted to keep this training set to have an underlying sample that would remain the same. Because with our machine learning processes, we can augment these balances and change them, but we wanted to keep that distribution that is from the survey itself, and that was challenging to do. So for example, we deleted duplicates that we found, but we tried to keep that underlying distribution to be the same. So number two, saving models themselves. So for example, one might save a scikit-learn model with Pickle, which is a Python-based serialization tool. And you can save these and use them later. It's very easy to use. However, there's no way to know what are in these files because they are serialized. They are unsearchable. So if you save things in Pickle, but you do not know what you saved in Pickle or who did this, if you're working on a team, or when or how, you have a problem because you don't know what it is. These also have security issues. For example, one should not open a Pickle file that was emailed to you, for example. And they can be slow, especially if you have something that's a very large model with a lot of weights and parameters in there. This could be very slow. So if we look in this space of, in this case, I'm using TensorFlow as an example, you have TensorFlow.save, model.save, you have model.save weights, and then there's all of these different ways that you can save models. Plus you have the different file formats like saved model, which is a TensorFlow proprietary format, or the classic HDF5, which I assume that ADAS folks are familiar with. And then you have these low-level versus high-level model type saving implementations. And these depend on your API. And so Keras has taken the world by storm in the past couple of years. So now their new models are added on to the quote unquote older versions of TensorFlow saved models, which are now deprecated. So my point to astronomers is these tools were made by people moving fast and breaking things, and they're not built to last on purpose. These are built for deployment in industry, and they're made to be used to predict car part sales or whatever. So clearly you're going to improve upon your model, and you're not going to keep something from the past that has been improved upon, which is not what we're doing in astronomy. We need things over time to be stable and to be replicable and reproducible for our work. And so my question is, what do astronomers need to save in models? And also, what do you not save? So we can't save everything. That is not practical. And so we might want to document these failed architectures, but not save them. We definitely want to save the models that we use for publications and document what is in these models, and then the TensorFlow version that it's created in. And this is more for transparency, because most likely we would not use the same model again in the future. We would probably find something that is better, or we would improve upon what we have. And so in terms of these gotchas, you might be thinking, why not put it all in a Docker container? Well, that's a good question. You could, but I have found in my experience, the learning curve is a bit steep with teams. Also, Docker is starting to charge $7 a month per person for teams. This is brand new. And for us in academia, this is hugely problematic. We're trying to use things that are free, right, or cost very little money. And this is a huge problem, the way that I'm looking at incorporating Docker into workflows. Again, Jupyter Notebooks might be nice as a recipe of steps, but again, Jupyter too has its own difficulties, has a very small group of maintainers, believe it or not, and is relying on a backbone of aging code. And so this is an issue. This has come up this week in GitHub. It's being discussed, what's going to happen to the Jupyter Notebook. And then obviously you have Microsoft, involved in these issues, and then Colab and other tools that have been adopted from this, and what does that look like? And so for add-on number 3, these additional artifacts. So FITS files aren't designed for machine learning. We know that. And there are tools like AstroPy that might help get FITS files and images into a model. But we could also put some of this information back into FITS to preserve it if that is something that people are facile with doing and they're familiar with the tools. And astronomers might need additional artifacts that are not needed by these machine learning practitioners, such as predictions per galaxy. Machine learning in the wild, in industry generally, aggregates are good enough. And in astronomy, uncertainty measurements rule the roost. These would not be something that is in machine learning traditional practices in the computer science realm. But hyperparameter choices and weights would be, so the combination of these would be something that astronomers might think about using. And then preserving this metadata piece associated with your study or your paper and put it in a place like Zenodo, which I assume most of you are familiar with at this point. We found in our work that a lot of people doing all of the tinkering and the trial runs didn't save what didn't work. And I feel this would be useful to save too. It's all of these things that someone else tried and it didn't pan out. Good to know for the future about why models would go awry and not give you the results that you're looking for. And also a breakdown of looking at what metadata is for your team and then what is for public use for reproducibility's sake. So in conclusion, the documentation is time consuming, but I think it's worth it. And deciding on these storage formats is important. Otherwise, you might have a Tower of Babel of models in these different formats. This is not optimal, especially 2 years down the line, people leave your group, you don't even remember what they did. It's in a pickle file, and we all know that's not good. Working and publishing in these cross-disciplinary spaces means accruing these different types of evidence that are necessary for ground truthing and results. And what does that look like for your team? And then, as I pointed out, these information preserving needs, they vary between what you need to save for yourself, for your team, and then what you're going to share with the outside world. And thank you very much. And thank you to the Sloan Foundation for funding our research and Spell ML for funding our machine learning runs. Thank you.
Bernie, thank you so much for a great talk. There's a hot debate going on Discord. I'm not sure if you're following there. I have a question from Jonathan Kenyon. Hi, Bernie. So you mentioned how challenging requirements and new technologies may make updating or changing a format necessary. Can you comment on the challenges you feel we face when attempting to make these changes?
I'm sorry, I didn't hear the first part of the question. Can you repeat that?
Sorry, he asked that you mentioned how challenging requirements and new technologies may make updating and changing a format necessary. Can you comment on the challenges you feel we face when attempting to make these changes?
Right. Well, for the astronomy community, I feel like everyone is generally used to a stable format such as FIT. You don't have that when you go into the machine learning space. And so to just be aware of that and to keep that in consideration is the point that I'm trying to make, is that these formats might go away quicker than you might realize, like TensorFlow.save or something. And so how do astronomers keep things in the way that they've always kept things is the question that I'm thinking about.
Okay. Thank you so much, Bernie. Another round of applause for her.
Thank you.